Okay, here we want to find the inflection points of the graph of the function f of x equals 6 sine x plus 6 cosine x, only on the interval 0 to 2 pi. Now, recall points of inflection. These are points on the graph where the concavity changes, whether it's a transition from concave up to concave down or vice versa. We're looking at places where the concavity changes. And the second derivative of the function is what tells us the concavity or the shape of the graph. So we're going to need to go ahead and take the derivative and then take the derivative again. We don't need the first derivative. That tells us increasing and decreasing and maximum and minimum points, but we need the second derivative. So let's say, okay, f prime of x is equal to, well, the derivative of sine is cosine, so that's 6 cosine of x, and the derivative of cosine is negative sine, so we'll have a minus 6 sine of x. And now we'll take the second derivative, f double prime of x is equal to, the derivative of cosine is negative sine, so that's a negative 6 sine of x minus a 6 cosine of x. Now, the graph of a function could change concavity where the second derivative is undefined, or when the second derivative is equal to 0. So let's go ahead and take the second derivative, set it equal to 0, and solve for x. So we want to know, we could add 6 cosine x, 6 cosine x to both sides of the equation, and we want to know when is negative 6 sine of x equal to positive 6 cosine of x. Or we could divide both sides by 6 and eliminate those. Or when is the sine function and the cosine function equal to each other but opposite in signs? Now if you go over to the unit circle, there are two places where that happens. At the angle 3 pi over 4, at the angle 3 pi over 4, we have the point negative root 2 over 2, comma positive root 2 over 2. And at the angle 7 pi over 4, again, the sine and cosine are the same number but opposite in sign. That would be a positive root 2 over 2 and a negative root 2 over 2. Okay, so the equation f double prime of x equals 0 has two solutions. X equals 3 pi over 4 and x equals 7 pi over 4. So now let's examine the sign of the second derivative. When is the second derivative positive or negative? Well, there's no discontinuities, there's no cusps, there's no corners, there's no places where the derivative or the second derivative would be undefined. So, the only places that this graph could change concavity is when the second derivative is equal to 0. So let's look at it this way. The second derivative, f double prime of x, and let's look at this from 0 all the way up to 2 pi. And let's cut this interval up into sub-intervals. So one of those places where we'll divide the interval is at 3 pi over 4, and one is at 7 pi over 4. Now we know the only places that the sign of the second derivative could change is at those two numbers. So if the second derivative is let's say negative for one number in this interval, it's negative for the entire interval. And if it's positive for one number in the interval, it's positive for the entire interval. So let's take one test value, maybe an easy value to work with. Let's say pi over 2. And let's choose a test value in the center subinterval. Let's use pi. That's a good one. And in the third subinterval, well, there's one special value. If we look over here at the unit circle, there's one special value between 7 pi over 4 and 2 pi, and that would be 11 pi over 6. So let's use 11 pi over 6. Okay, so we want to know what is the second derivative evaluated at pi over 2, the second derivative evaluated at pi, and the second derivative evaluated at 11 pi over 6. We're not so concerned with what the actual values are. We're concerned with whether they are positive or negative. Okay, our second derivative now, don't forget it's up here. This is the second derivative. Negative 6 sine x minus 6 cosine x. So if we plug in pi over 2 for x, we'll have negative 6 times the sine of pi over 2, which is 1, minus a 6 times the cosine of pi over 2, which is 0. So that will give us overall a value of negative 6. So in this interval, the sign is negative. If we plug in pi, let's see, we'll have negative 6 times the sine of pi, which is 0, minus a 6 times the cosine of pi, which is negative 1. So an overall value, 0 minus a minus 6, or 0 plus 6. So that test value gives us a positive result. And finally, 11 pi over 6. So negative 6 times the sine of 11 pi over 6. And the sine of 11 pi over 6 is negative half. Minus 6 times the cosine of 11 pi over 6, which is positive root 3 over 2. So this is a positive, this is a negative, but the negative is the negative is more negative, let's say, than the positive. So if you pop this into the calculator, you would get a negative number for sure. So that third subinterval is negative. So what this tells us is on the interval 0 to 3 pi over 4, and also on the interval 7 pi over 4 to 2 pi. That's this interval here and this interval here. The test value gave us a negative result. When the second derivative is negative, the graph of the function has a shape that is concave down. And on this center interval, let's make it look like this. On this center interval, the sign of the second derivative is positive. So on the interval 3 pi over 4 up to 7 pi over 4, the graph of our function has a shape that is concave up. So we have a change in concavity at 3 pi over 4, which means there's an inflection point. Inflection points. So let's say there's an inflection point at 3 pi over 4. And there's also an inflection point at when x is equal to 7 pi over 4. And so remember, anytime you're looking at a specific point on the graph, if you're plugging in an x value to obtain the corresponding y value of the point, you always plug in back to the original function. So if we want our inflection points, we plug those x values back in here to the original function, 6 sine of x plus 6 cosine of x. And since the sine function and the cosine function are opposite in sign but equal in value, if we plug in 3 pi over 4, we'll get 0. And the same thing with 7 pi over 4, we will also get 0. So those are the inflection points. So let's use a yellow highlighter here. Our answers, we have our intervals of concavity, and we have our inflection points. Now, the last thing I want to say about this is just you have to be real careful with the notation. This is one of those really annoying aspects of mathematics where we're using the exact same symbol to mean two different things in the same problem. So, parenthesis, comma, parenthesis. Up here, these are intervals of numbers. So 0, parenthesis, 0, comma, 3 pi over 4, close parenthesis. That means all numbers between 0 and 3 pi over 4, not counting 0 and not counting 3 pi over 4. Over here, the inflection points, same notation, parentheses, but here it's x value, comma, y value. So let's say points, and up here, intervals. So I'm sure at this level, everyone understands the difference between a point and an interval. I just wanted to sort of make a point of just pointing that out. I'm using the word point a number of times there in the sentence, but just keep an eye on the context and the symbols we're using. Okay, that about does it for this problem.